Well, I think we'll go ahead and resume here.
Yeah, no, I just need to talk about the facility.
Is in solving the same problem with removing mercury from my drainage. And they were specifically tasked with looking at chemical additions. In wastewater treatment, there are also problems with heavy metal removal, and there are some novel chemicals that have been introduced to that. And the neat thing about this team is that I didn't even have to direct them to that literature. They found it themselves and optimized that. So with that, we'll turn it over to ChemTrails.
Perfect. Well, thank you, Dr. Urban. Good morning, ladies. Good morning, gentlemen. My name is Anthony Bang. With me is Stephen Bang and Eric Priscilla, and we are ChemTrails. Today, we're going to be talking about mercury treatment through chemical precipitation. As a quick outline, we'll talk about the introduction and scope of our work project. We'll also talk about our chemical additive research we did as a group, our software simulation and results, our chemical additive proposed plan, design assumptions we made as a group, our treatment facility and structure design, as well as the cost and schedule of that. Then we'll also talk about the sustainability factors in our project, our impacts our project has, conclusion, recommendations, and time for questions. So, as another quick introduction, we're all at Elm Creek, particularly near the old Osceola mine shaft. Of course, you know that Elm Creek has a mercury problem, as it was listed in 2002 ChemTrails for its mercury levels. So, the scope of work, we needed to identify the chemical addition to remove the mercury, as well as identify the sustainable power options as we want our project to be long lasting as well as sustainable. We also need to identify the structures needed for our treatment facility. Then, of course, identify the waste release as well as ways to dispose of that waste. For the stakeholders for this project will be the River Snow users, Hellhound, Break, Trap Rock, River, and Horse Lake, as Hellhound Creek is a tributary to those bodies of water. Then, of course, the local community, specifically also the township, as will be affected by the treatment facility and then, of course, people.
So one of the first steps in our design process was we had to find chemicals that we wanted to use. And this is kind of a list of all of them, and some of the ones in bold, specifically alum coagulation, like the previous group used, and the novel chemical that Urban mentioned, which is, we call it DDAT, the full name of it, and chemical formula is also there. All the other options, we kind of decided not to use for reasons that the other groups also specified, primarily that either really high doses would be required and that could get pretty costly, or because it just wasn't really able to reduce mercury down to the levels we needed. The last two options we looked into were like filtration ideas, and then we kind of decided that was like outside the scope of our project and would not be needed. So as I've already said, we're gonna ultimately choose alum coagulation along with a BDET precipitation in our treatment plant. And in order to simulate this, we used Visual MINTEQ, which is basically just a water chemistry software where you input your known, or in our case, we predicted some like water parameters along with temp, pH. And then I also had to add BDET into like the software of the program, which is shown on the next slide. Disclaimer, don't read that. That's a lot of jargon for those of us that aren't chemistry savvy. You'll see over in here, if I can, no, over in there are the log K values, which I kind of explain at the bottom. They're really just the reaction constants of BDET with the other water chemistry parameters. So a higher value there is basically showing that that reaction is more likely to proceed right, which is what we would want. So one of the first runs I did, these were some of the parameters I input along with the previous reaction constants that were shown. Ultimately, we found that most of the BDET that we were adding was combining with calcium rather than mercury, which isn't what we expected. We kind of concluded that ultimately this was due to the setup of the MINTEQ software and the log K values we use. However, this first run with a pretty high dose of BDET, we ended up reducing mercury down to 40.1 nanograms per liter. Later on in the semester, we did another trial with updated. A lot of these values have changed from the previous trial based on Team 1's sampling that they conducted, and we kind of got updated results. And in this trial, we basically ran the same thing again. I updated the calcium and copper log K values for BDET. We did more research and figured they should probably be lower than I initially suspected. So in this case, a lot less of the BDET bound with calcium. However, it didn't really help our results, if you will, because the final effluent mercury concentration was still 41.3 nanograms per liter, which is actually an increase. So as a summary, the binding constants didn't really do what we were expecting them to do, which was interesting. Kind of an explanation for this is a PC pH diagram, and if you look at like the topmost of the graph, you'll notice from pH 3 and greater, that topmost line is orange, which represents HgOH2, and below pH of 3, the most dominant form of mercury species is Hg plus 2. So, as is explained in the bottom here, when I set up the MINTEQ software, I was, if you will, reacting BDET with Hg2 plus and had a log K value of roughly 30 for that. However, at the mine drainage pH of 8.5 that we use, you'll notice a lot of other groups use like 7.5, which is what it is like coming right out of the mine drainage. We used 8.5 because we assumed that that was like super saturated with CO2, and it probably, as you left it exposed to the air, like increased more to like 8.5. Anyways, the main purpose of this slide was to show that in reality, the BDET was trying to bind with HgOH2 and just wasn't as effective as perhaps we were expecting it to be. So the third trial, these were ultimately our final results. The gray line in like middle there, you can see with the dots, were 3 different trials we ran with varying BDET doses. And I should note that we didn't actually add alum or simulate alum in this simulation at all. So I kind of just added a factor of safety. Pretty conservative estimate, as the other group noted. Alum itself there's research to show that it could likely reduce mercury down to like 80% of the initial concentration. So ultimately, we're going to propose a 55 pounds per year dose of BDET. And then that bottom red line is the water quality standard of 1.3, which I should note is it's not a drinking level value, it is the water quality standard for wildlife, which would basically mean that those fish don't have consumption advisories. So as I've already said, we're gonna propose a 55 pounds of BDET and 55 pounds of alum, which is equivalent to those doses, about 70 grams per day. And this is based on a maximum flow rate. Out of all the flow rates we were given, the maximum was 5.12, when in fact, as Team 1 said, the average is more like 2.0. Our treatment facility is also going to treat via like a variable flow throughout our plant. So we're going to measure the flow at each stage of the process, and that way it kind of avoids the need for like a giant like retention basin, if you will. We also, for this simulation, used an influent concentration of 127 nanograms per liter, which were some of the older, I want to say 2001, 2002 values that were measured in the mine drainage site, when Team 1, as of recently, measured it to be like 38 that should be nanograms per liter. That's a typo there, which suggests that maybe the mercury concentrations in the mine over the last like 20 years have decreased. Yeah. Just some general like design assumptions we had to make in order to get to these conclusions was that the water chemistry and general quality data that we were given along with flow rates were accurate. We also assumed that all of the mercury is in the form of Hg2+, which, as I said, was perhaps not the best assumption and ultimately influenced our results.
And for
And we also assumed there was no significant variation in water chemistry. I already said that. And a constant temp of 10 degrees Celsius.
So for the treatment facility, as will be discussed later, some assumptions we made were that the alum and flock size and settling velocity used were accurate for the resources we used, and that the velocity gradients and detention times would be similar to common water treatment values, and also that nearby wetlands not protected. So this is the general process of our treatment facility. As Ethan said, we designed for variable flow, and we will have meters throughout the facility measuring the flow and concentration of chemicals in order to adjust accordingly. And so starting at the top, go from mine drainage to the retention basin and weir, then to the splitter box. From there, that chooses which branch of the facility it will go down. There's two. Then there to the rapid mix tank and slow mix tank, then sedimentation basin, and then back out into the creek. So then here's just another overview of it. As you can see, starting here, going to the splitter box, then it goes down these two different branches of the facility. We designed for two different branches just in case we needed to take one down for maintenance, and one side should be able to treat maximum flow. So first thing we designed was the weir and retention basin. And the purpose of this is to give enough head to begin treatment process under gravity flow, as well as just give the water a good starting point to get into the splitter box from. And design considerations for this were the maximum flow and maximum head. And the important thing here was under maximum flow, you wanted the head of the basin or the head of the flow not to exceed the walls of the weir or the walls of the retention basin. And so we've calculated the maximum head at max flow to be, max head's 1 feet, which accommodates the max flow. And then it passes these conditions. That was the design for the weir and retention basin. And then onto the rapid mixer. The purpose of this is to inject the beta and alum chemicals. We went with a conventional stir tank with a vertical shaft turbine mixer. Design considerations here were the detention time and velocity gradient, and we used standard water treatment values for this, which were this 30 and 1500 value up in the right-hand corner. And we also considered stirred tanks versus other devices, and some advantages of the stirred tank over other devices were some were expensive and subject to clogging. So with a system that you want to be hands-off, you don't want someone there checking for clogs. Yeah, and then also note, our design flow for this was really large because we didn't get the data until late in the semester. So we put on a large factor of safety to account for spring melt and where we thought the flow might be higher. And that is a picture of our rapid mixer. So now onto the slow mixer. Purpose of this is to promote flocculation. Considerations like the rapid mixer are the detention time and velocity gradient. And we use standard water treatment values for cold climates. Also, considered the mixer type, which was a vertical shaft turbine. And advantages of this were that had no head loss, provided excellent operational flexibility, which is nice for a variable flow system, and had low to moderate maintenance. Other considerations were the number of trains and compartments per train, which train is just like different, well, this is one side of a train and this is another train. The flows in parallel. So, and then, yeah, okay. And so then for our sedimentation basin, the purpose of this is to set out the alum flock, as well as collect sludge from the system and bring it to the dewatering box. Considerations here were the settling velocity of the alum floc. And for this, we found that our slow mix tank found a source that said the way it was set up would create medium dense particles. And then another table said that it would settling velocity would be about 0.003 feet per second. So that was what we used in our design. We also considered the shape of the tank. We went with a circular tank because these can provide less mechanical issues since there's less moving parts underwater, as well as you can use less concrete in making the tank. So they can be cheaper than rectangular tanks. And again, this is also ends up being larger than we need to because we used a really large flow rate. So yeah, sedimentation basin, see the sludge will collect on the bottom, it gets scraped out and then gets drawn to the center and then goes out to a dewatering box and sludge, where the sludge will be collected and taken for waste.
All right, now looking at the cost, this pie chart here is showing our construction costs. So we're looking at about $2 million. The biggest portion from this pie chart would be the solar panel installations. The reason for this is that the solar panels are actually going to help pay the cost of the facilities throughout the coming years. So after that, then the biggest cost will be of course, the treatment facility itself. We have to have the tanks as well as the sedimentation tank and the quantization construction. After that, then we also have miscellaneous water facility items and the temporary water diversion. And we had used RS means as well as online means to find some of our cost estimates, especially with the propellers and motors. Now looking at our construction schedule, we have chosen a date for next year, early April. We would send a mobilization and a survey team out there to ensure the site was prepared for construction. And then around mid-April, we'll then begin to start clearing and grubbing, ensuring the site is ready for the construction phase. About the end of April next year, then we'll start doing the biggest portion of the construction phase, which is the construction of the treatment facility itself. This would include the excavation, the foundation, walls, concrete pouring, as well as curing, and then of course the mechanical components installation. Once that is completed, then we'll also look at the miscellaneous water items near the beginning of July, which will consist of the solar panels, the piping, the pump and feeder station, as well as the sludge filtration. And then we should be completed in the 6 months at late August. So now looking at the cost for the annual operating costs, we're looking at about $250,000 a year. The biggest one would be the unit itself, as we are putting BDA and a run to the mine drainage. So we need a set supply of that to ensure that we are actually treating the water. After that, then we're looking at the solar panel beautification, but again, the solar panel is going to be acting as a sustainability as well as things that the facilities for throughout the coming years. After that, then we're also looking at the maintenance and then the water quality cycle, and we want to ensure that the mine is actually treated, and then we're sending the water back better than the keep. And for the sustainability, solar like I talked about, the solar panels is our sustainability component of our facility. We reached out to Jay Melvin, the director of the Juvenile Research Center, and he directed us to this website, and also talked about how solar panels are beneficial, which it would decrease our carbon footprint as well as be able to provide 100% of our required electricity. And if the project was taken up by a municipal government, then they can possibly take that power and send it back to the government.
So this is that PV Watts website, and this is just a little example of what you can expect if you go there. So for inputs, you're going to size solar panels. You put the location, because of course sun varies from wherever you are. Solar panel type and size, and that's just to figure out if it's going to produce enough electricity. System losses, the tilt of the solar panels, and the cost of your power in the area. And then outputs, it's the solar radiation provided for each month in your location, as well as the AC energy produced and the value, which that would depend on what your local utility is charging for the electricity. And this was our results for our solar panel calculation. So at the top, we have what UPPCO will pay for a for a system that's connected back into the grid that will re-inject the power. And for the first 5 years, these are the numbers available on their website. It's a fixed cost written into the contract. And so that amounts to about $0.04 per kilowatt hour, which is less. They buy back the energy less than they sell it for, which that's kind of important to note. And so then using that, you look at the price of hookup charge and income from selling power. So I assume that we could, for the full system, that 50% of the power would be able to be sold. So since the tanks won't always be full, so they won't require the full power the whole time. So then this is the income from selling that power, and then minus the charge of the hookup. And then, so then this is the final cost of the connection per year. And then this table at the bottom kind of brings it all together. Then that you can see that the best value was having solar panels that were capable of producing 100% of the required electricity, and while still being connected to the grid. Being connected to the grid is beneficial because you don't need batteries, which have high initial costs, as well as I found they need to be replaced about every 10 years. So that's really what hurts like this net present value. And it should be noted that this doesn't take into account like the whole construction of the project. This just takes into account just the power costs. So the net present value of the whole project would still be negative, which is to be expected.
So the impacts that our project will have, the first part, mainly want the water quality to be better for us, as we have been working on this project for this whole semester. Secondly, the water treatment facility will be built in the local community, so it can be seen as a just like I think the numbers, but of course we want our treatment facility to be a benefit for the community. With that being said, the treatment will use waste, and we will be able to dispose of that waste and make sure that the waste is not being introduced to the environment, and make sure the waste are going to designated landfills. And in conclusion, we believe that the construction costs are within reason. Of course, the biggest thing was the solar panel installation, but of course, the solar panels will pay the cost during the coming years. And VITA shows a lot of promise, but it's still relatively new. So, with that being said, VITA was engineered specifically to bond with Berkeley. So, we think that VITA has a lot of promise, and that the project can be feasible just from this.
As far as like next steps or recommendations, we definitely need to do more research into BDET, whether it's the pilot scale test or just like general lab testing. Michigan Tech should soon have approximately 5 grams of BDET that we would be able to use for lab testing, where we could determine like settling velocities and particle sizes and actually be able to more accurately simulate like treatment effectiveness. Also, as I've already said, like the MINTEQ software was kind of being funky, so maybe if we could find a different software simulation that could more accurately simulate our treatment. Also, maybe even like more research into the reaction constants, the log K values that I used would definitely be helpful. And we had a pretty good estimate of the mercury concentration of the waste. Unlike most other groups where they have like massive amounts of soil that they have to get rid of, we have only like 130 pounds of waste generated each year. So that is likely going to be considered hazardous waste. So it'll have to go to a special landfill. Other recommendations as far as like just general site information. As most groups have said, we definitely need more water chemistry and flow data like collected every month throughout a whole year. So that'll help us better predict flow in an average flow. Even just like soil and subsurface conditions for as far as like building an actual structure there, the groundwater table, that would be super helpful. And for the purposes of our project, we ignored any sort of like land or project ownership items, like property lines and those sorts of things. We would also like to look into the Michigan Stream Quantification Tool, or SQT, and we were kind of wondering if this could save on project costs, if the remediation of the stream if those credits could be like sold back to someone else as a way to save on costs.
Questions?
All right, so was that correct that after sedimentation, you were just gonna collect your sludge and transport it outside?
It goes to a dewatering box where it's pressed, and then
What percent solids will you?
I don't believe we actually looked into that too much. We just kind of said like, this is how much beta and alum and mercury we expect to have removed. It's like, that's how much waste we're gonna create. We didn't look into actually designing the dewatering box.
Right, because that can be very costly. Water is very expensive to transport. So I was curious as to the logic there in terms of did you have someone who take that as or the slurry, you know, is it something that you had actually get you the
it'll be dewatered.
Other question?
So I thought the new chemical is really interesting in that I'm wondering, like, is it, when you receive it, is it solid at room temperature and then you dissolve it in the water? Yes, okay.
No, I'm not totally sure, but I believe when we receive it, it's already dissolved into a solution. One of the main authors from the articles related to this chemical, I was talking with him all semester about just like general information about it, and he had told me what it was dissolved in, but I would have to go back and look. I don't really recall right now.
So I'm just wondering about handling of it, like for safety also. Is it redox sensitive with oxygen? So would it lose its effectiveness as it's stored and mixed into the mixing device?
If I'm being totally honest, we're not sure. It's still very much in like the developmental phase, and we only found a small handful of articles that it was being used to specifically address like mine drainage in Alaska. So to answer that question, I'm not totally sure.
Well, I just want to say that's really neat how you incorporated those reactions into the chemical equilibrium program.
Okay.
So I was curious about a little bit distracted. It sounds famous, but the cost of solar power was like what, 2/3 of the whole project, or a little bit more than that?
Yeah, it was like 60% or something. Let's see.
70%.
Yeah, or 60, yes, 66%.
So what were was there other options for powering that?
Well, you could just not use solar panels and just have a hookup to, UPPCO.
And how different was the capital cost of that?
As seen on the bottom, the zero, this is the net present value of just paying UPPCO over 25 years, which is the life of solar panels, 25 to 30 years. So there was about a little bit over $1 million difference.
But there's always a difference too when you look at 25 years, you gotta pay now, right? So your capital expense is gonna happen right now if you go with solar option. You don't have the capital, it doesn't really help that it's gonna make it for 25 years. So I guess related to that question is, how much uncertain is that payback period? How certain are they solar panels and their payback potential? But also, doesn't that depend also what's going to happen to the electricity prices and all that stuff? Did you do any sensitivity analysis for that?
Yeah, it depends on just what the power costs are, if they would pay back or not.
Are they fairly certain on how much you can actually collect with the solar power on annual basis? And
yeah, so using, I use this and it just estimated. So annually, 25 years out, I guess can't really say, but from month to month, this is This is what I use to estimate what we collect with solar power.
I think what he's meaning to ask is like, how do you know, like, how accurate these results are?
So typically, when you look at, I mean, when you're looking at capital expense, so you're gonna be trying to, I think it's great to look at it, but I think you're always gonna look at it with a little bit of you're gonna leave some asterisks if it's a fairly new technology and if there's a lot of other uncertainties and computer code as well.
Okay,
Because the cost today, you gotta pay, right?
right.
And you're leaving the chance to there's some risks involved, so at least
Okay.
acknowledging that is.
Okay, makes sense. Oh, man.
Are we still open for questions?
Oh, yeah, we're still open for questions.
Hello, this is Jay Parent from Eagle. I'm the Water Resources Division District Supervisor in the Upper Peninsula. I'm the new Steve Casey, I guess. Great job, everyone. Those presentations, I had a few other things I didn't follow through. I thought it was a great job by everyone. Wasn't too long ago that I was in your seat in Noel's class, so I know what it feels like. Couple thoughts, I guess. So we started off with wetlands treatment. You know, here at the DEQ, we really look at the bioavailability of the mercury. You know, what's the big picture? What's the problem? It's getting into fish. Well, that means it's getting in the food chain. And by putting mercury into a wetland, you know, you really got to worry about putting that into the food chain. It's just a thought. For the other two technologies, active treatment, did you guys find anywhere else in the country that they're doing this with mine drainage? Did you have something to look at?
This is a question for any of the other teams. What did Eric say he had done in terms of mining?
I think we were like going to do projects and then canceled or something, like we did not find a lot of well treatment systems, but most of them were thermally pure. It's like people
Right, I didn't get that because the audio wasn't that well for online, but you know, I think that would be something to look at, and the costs were interesting too. Something was done this kind of stuff. You know, the costs are really going to depend on who's going to run it. Did you figure out? Did you include that on who's going to operate and maintain this? Is it going to be a consultant? Is it going to be an authority? Is it anything like that?
We didn't specifically say if it was going to be an engineering firm or municipality, but we just put a cost of labor into our operation costs. But no, we didn't specifically take into account who would be treating it or maintaining it.
All right. I guess I don't have any other questions. It's interesting to watch this, and you know, everybody in the class will soon be 15 years into engineering or some other field, and you guys will learn a lot, and good job, and hope to see you out on some projects, I guess.
Thanks a lot, Jay. And yeah, we'd be happy to talk in more detail with you. We've got to move on at the moment, but thanks for attending and for your comments.
Cool.
So at this point, we'll change over. That completes the Osceola mine reclamation section. And next, Hansi will run the show here with the next set of talks. So I will be
Yeah,
ending
you're
the,
gonna- We have a different link, so you can stop the recording and enter.
we have a different link.